Have you ever really stopped to think about how you move? I mean, how a simple thought like, I'm going to pick up that cup, actually becomes a physical action. Well, today, we're going to trace that exact journey. We're following the command pathway all the way from that first spark of an idea in your brain, right down to the muscle that does the work.
And to guide us, we've got a real-world medical mystery. Picture this, a 74-year-old woman goes to sleep perfectly fine, but when she wakes up, she can't move the entire right side of her body. Her speech is slurred, there was no accident, no warning at all. So, what on earth happened inside her nervous system?
To figure this out, we have to basically become neurological detectives. We're going to follow the trail of a single motor command, step by step, down the superhighways of the body. Because if we understand the normal route, we can figure out exactly where the roadblock happened.
So where does our investigation start? No surprise, it's up in the brain. But not just anywhere in the brain. We're zooming in on a very specific, very important strip of neural real estate. This is the headquarters for every voluntary move you make.
And here it is. See that highlighted area? That's the primary motor cortex. Think of it as the mission control, the CEO's office. This is where the final go order for any movement is officially given and sent down the line.
But hold on, before that go signal is ever sent, a ton of planning has to happen behind the scenes. That's the job of these areas right next door, the motor association areas. They're like the strategists who design the whole movement, figuring out the sequence of actions and the timing before mission control hits the launch button. Now, this is where it gets really weird and cool. The brain's command center isn't organized by the size of your body parts. No, it's organized by how much control they need. This bizarre map is called the motor homunculus, or little man. And look at it. The hands and the face are absolutely enormous, right? That's because they need incredibly fine, detailed control for talking, for expression, for using tools. The back and legs, they make much simpler movements, so they get way less brain space.
Okay, so the plan is made. The command is issued. Now that signal has to travel. It leaves the surface of the brain and starts this long, incredibly fast journey deep into the brainstem.
And this is the main road it takes, the corticospinal tract. It's basically an information superhighway, this massive bundle of nerve fibers that forms a direct, high-speed connection from the cortex all the way down to the spinal cord.
So let's trace the first leg of the trip. The fibers start by fanning out from the cortex, kind of like a crown. They call it the corona radiata. But then they get funneled and squeezed together into this tight, critical choke point called the internal capsule. It's like a crazy busy intersection where all the traffic has to merge before it dives down deep into the brainstem.
Now, up to this point, our signal's been traveling straight down, on the same side of the brain it started on. But our journey is about to take a really sharp and, frankly, a very famous turn. This is the plot twist that explains so much about clinical neurology.
Right, so before these commands can actually get to your arms and legs, they approach this crucial border crossing at the very bottom of the brainstem. And what happens right here? Well, it's the key to solving our entire mystery.
Get this. An overwhelming majority, about 85% of all those motor fibers we've been following, are about to do something that seems totally backward. They're going to switch sides.
And this is the exact spot where it happens. It's called the pyramidal decussation. The fibers bundle up to form these structures called the medullary pyramids, and then, bam, they cross over to the other side. This is why your left brain controls the right side of your body, and your right brain controls the left side. It's a fundamental rule of the nervous system, and it all happens right here.
So, after that great crossover, our signal is now in the spinal cord, and it's on the opposite side from where it began its journey. But even down here, the highway splits into different lanes for different kinds of jobs.
You can really think of it as two different systems. You've got the lateral system, that's the main highway we've been following, which controls all the fine, skilled movements of your hands, arms, and legs. Then you have the medial system. This is made up of the fibers that didn't cross over, and its job is to manage your core muscles for posture and balance. It's less about details and more about keeping you upright. And you can see that division right here in this cross-section of the spinal cord. It makes perfect sense, right? The lateral tracts are out on the sides, perfectly positioned to send signals out to the limbs, and the medial tracts are closer to the center, where they can manage the big muscles of your trunk. Okay, our signal's epic journey is almost done. It dives into that butterfly-shaped gray matter in the middle of the spinal cord, and it finally hands off its message. This is like the final baton pass in a relay race. It connects with the lower motor neuron, and that's the one that sends its own signal directly to the muscle, and, at last, makes it move.
So there you have it. We've traced the entire path, from a simple thought to a real action. Now, let's go back to our patient and use this new roadmap to crack the case of her sudden paralysis.
Think about it for a second. The clues have been there all along. The problem is on the right side of her body. Based on the path we just followed, what does that immediately tell you about where the damage has to be? Let's just break it down. Her symptoms are on the right side. We now know for a fact that the commands for the right side of the body start in the left side of the brain, all because of that great crossover. So the conclusion is simple. The damage, which was probably a stroke, had to have happened on the left side of her brain. And more specifically, it had to be somewhere above that crossover point, blocking the signal right after it left headquarters. Case closed.
So we've mapped out the main highway, the direct route for getting a command from A to B. But this is just one piece of the puzzle. What about all the other systems, like the cerebellum and the basal ganglia, that are constantly working in the background to smooth out our movements, to make us graceful instead of just clunky and robotic? Well, that's a whole other journey for another time.